In this video, I'm going to look at everything that you need to know for integrating with partial fractions for A-level maths. So first off, we need to establish when do we need to use partial fractions to integrate. So let's have a look at our first question here. So we've got the integral of a fraction. Now let's go through our methods for integrating fractions and rule some of them out. So in my numerator, I do have multiple terms, the x and the subtract 5. However, because the denominator is also multiple terms, splitting the fraction up into multiple fractions with the same denominator probably isn't going to be the most effective strategy. Then we could consider using indice laws instead. However, our denominator is raised to the power of 1. So if I used indice laws, I'd have a power of -1 when I rewrite it as our numerator x subtract 5 multiplied by our denominator x squared subtract x subtract 2 to the power of -1. And we don't want a power of -1 when we're integrating, so therefore we don't want to use indice laws. Now once we've ruled that out, we could consider the natural logarithm and the reverse chain rule. To check if we can use that, we take our denominator and we differentiate it. So that would give me 2x subtract 1. Then we compare what we've got here with our numerator and try and see if they're numerical multiples of each other, which they're clearly not. Because to get from 2x to 1x, you'd have to multiply by a half. But to get from -1 to -5, you'd have to multiply by a different number, which would be 5. So therefore, they're not numerical multiples of each other. So we can't use the natural logarithm and the reverse chain rule. So we've ruled that out as well. Then we should consider, do we have an algebraic improper fraction? Now to check that, we look at our numerator and identify the highest power of x, so that would be a power of 1. Then we look at our denominator and identify the highest power of x, and that is a power of 2. So the highest power in the numerator is not the same as or greater than the highest power in the denominator. So therefore, it's not an algebraic improper fraction either. So we've ruled out a lot of methods, so we're going to have to consider what can we do once we've ruled those out. And our next option is to consider rewriting our fraction in terms of its partial fractions. Now when we can do that is when we have a quadratic or cubic denominator, which we can factorize into linear factors. So if we look at our denominator, it's a quadratic. Now let's have a go at factorizing this into linear factors. So I'd get the integral of x subtract 5 divided by, and that quadratic can be factorized as x subtract 2 multiplied by x plus 1. So therefore we've successfully factorized it into linear factors. So now we can have a go at rewriting it in terms of its partial fractions. So what I would do is take our fraction, x subtract 5 over x subtract 2 multiplied by x plus 1. And I could rewrite this as a divided by one of our linear factors in our denominator, so we could say the x subtract 2, plus b divided by our other linear factor x plus 1. And the a and the b are just constants. So what I'm going to do next is try and add the fractions on my right hand side together. So to do that, I need a common denominator. So what I'm going to do is take the x plus 1 from over here and multiply on the numerator and denominator of the other fraction by x plus 1. And then I'm going to take the x take 2 from over here and multiply the other fraction on the numerator and denominator by x take 2. Like that. Now let's write out what we get. So I would have a multiplied by x plus 1 divided by x plus 1 multiplied by x take 2, and then plus, and it's going to be b multiplied by x subtract 2 divided by x plus 1 multiplied by x subtract 2. Now I can add my two fractions together because they have the same denominator. So the denominator stays the same, and then my numerators get added, so I'd have a multiplied by x plus 1 and then plus b multiplied by x subtract 2. And then this is identical to the original fraction I was working with, so that's x subtract 5 over x subtract 2 multiplied by x plus 1. Now these two fractions should be identical to each other, And as you can see, the denominators of both fractions are the same. So therefore, the two numerators should be the same as well. So x subtract 5, my numerator on the left, should be identical to the numerator on the right. So the a multiplied by x plus 1 plus b times x subtract 2. So now we're going to have to consider how we can find a and b. Now the idea is this here is an identity. Now what an identity means is that if I substitute any value in for x on the left hand side here, I should get the same result as if I substituted that value of x on the right hand side over here. So I need to pick an x value to substitute into both sides, and to pick that x value, we're going to consider what would make my brackets on the right hand side equal to 0. If we consider this bracket here, x plus 1, well, when x is equal to negative 1, that bracket would be 0. So let's substitute x equals negative 1 into both sides of my identity. So on the left-hand side, we would have negative 1 subtract 5, so that would be negative 6. And that's going to be equal to, when I substitute negative 1 onto the right-hand side. So as I've already discussed, if I put negative 1 into this bracket, I'm going to get 0. So I'm going to end up with 0a, which is just 0, so we can ignore that term and just focus on my other term. Now when I substitute negative 1 into this bracket, I would have negative 1 subtract 2, so that would give me negative 3. So I'm going to end up with negative 3 lots of b. So now I can use this to obtain b by dividing by negative 3 on both sides. So I would get that b is equal to positive 2. Now let's focus on how we're going to find a. And to do that, we're going to have to consider, what do I need to substitute into this bracket here to make it 0? Well, if I have x subtract 2, I would have to substitute positive 2 in to get 0. So we're going to consider when x is equal to positive 2. So if I substitute that into my left-hand side, I would have 2 subtract 5, which is negative 3. And then on my right-hand side, if I substitute 2 into this bracket, I would have 2 plus 1, which is 3. So we get 3a. And then if I substitute 2 into my second bracket, we know we get 0. That's why we picked 2. So we're going to end up with 0b. So we can ignore that term. So now we have an equation which we can use to find a by dividing by 3 on both sides. So we would get that a is equal to negative 1. So now we can go back and write out our partial fractions. So now what I can do is go back to this statement here, and I'm going to replace my a and my b. So I'm going to rub out my a and rub out my b. Okay, and a has come out as equal to negative 1. So I'm going to put that here. And then my b has come out as positive 2. So we're going to put that up here. So what I can now do is go back to my integral and rewrite the fraction in the integral in terms of its partial fractions. So I would get the integral of, and it's going to be the negative 1 over x take 2. And then plus our 2 over x plus 1. And because we got multiple terms, I should put it in brackets and then write the dx out here like that. But now what we can do is focus on integrating each of our fractions individually because they're separated by addition. So let's start with this fraction here, and let's consider which method of integration we're going to make use of. In the numerator, I've only got one term, so I'm not going to split this fraction into separate fractions with the same denominator. Now, if we look at our denominator, it's raised to the power of 1, so therefore we don't want to use indice laws because we're going to get a power of negative 1, which we don't want when integrating. So then let's consider our natural logarithm and reverse chain rule. So to do that, I'm going to take my denominator and we're going to differentiate it. Okay, so that's going to give me positive 1. And then we're going to compare this to my numerator, negative 1, and ask ourselves, are these numerical multiples of each other? And yes, they are. In order to get from the 1 to the negative 1, I would have to multiply by negative 1. Therefore, we can use our natural logarithm, and this negative 1 is going to form part of our answer, because our answer is going to be the natural logarithm of the modulus of my denominator x subtract 2. And we just have to multiply this by the negative 1 I found here. So I'm just going to put a negative 1 in front like that. So now let's consider my second fraction. And what you'll find is we'll be able to use a similar method for this one. And in general, when you do partial fractions, most of the time, you'll end up using the natural logarithm to integrate. Because if I differentiate my denominator x plus 1, that is going to give me positive 1. And then if we compare our positive 1 to our numerator 2, they are numerical multiples of each other. We'd have to multiply by 2. So we're going to make use of that in my answer. So I would write the natural logarithm of our denominator x plus 1 in modulus symbols, but I'd have to multiply by positive 2. So I'm going to write a plus 2 in front like that. And then all I need to ensure is that I have a plus c out here, and we completed our integration. So what I now need to consider is how can I simplify my answer. Now, because both of them involve the natural logarithm, I could potentially try and use log laws. Now, in order to do that and combine them into one, I'm going to start by bringing the 2 in as a power on my second logarithm. So I would have negative 1 multiplied by the natural logarithm of the modulus of x subtract 2, and then plus, and then we're going to bring the 2 in as a power. So I would have the natural logarithm of x plus 1 squared plus c. So now that I've brought the power in, we can now recognize that we have a subtract in front of this logarithm here. So therefore we can use our subtraction law of logarithms, and we can take what is in the positive logarithm, so this one here, the x plus 1 squared, and divide it by what is in the logarithm being subtracted away, which is the x subtract 2. So I can now write this as a single logarithm. I can write the natural logarithm of the modulus of, and it would be the x plus 1 squared divided by the x subtract 2, like that, and then plus c. So now that I've written that as a single logarithm, I could also consider how I'm going to get the plus c into the logarithm as well, because plus c is the most straightforward way of writing a constant, but I could also write a constant as the natural logarithm of a different constant, which I might call d. So I could say where c, our original constant, is equal to the natural logarithm of d. And then if I write out the rest of my statement, I'd have the natural logarithm of the x plus 1 squared over x take 2. And now we have two logarithms being added together, so therefore we can use our addition law and we can multiply what is in our logarithms together. So I'm going to multiply the d into my other logarithm. So I'd have the natural logarithm of the modulus of d multiplied by x plus 1 squared over x subtract 2, like that. And that would be as simple as we can make our final answer. Now let's consider a definite integral based off the working I've done so far. So now we've got ourselves a definite integral reflected by the fact that we have limits on our integral written here. But we do have the same fraction as the previous question, so we can make use of what we've done. What I'm going to do is say that this integral is equal to, and I'm going to write in square brackets my answer from the first part, which is the natural logarithm of the modulus, and we can drop the constant d, given that we're dealing with a definite integral, and I would just write x plus 1 squared divided by x subtract 2, like that. Okay, and then I'd close my square brackets and put my limits on the outside, 4 and 3. Now what we need to do is substitute my limits in, so we'll start with the 4. So I'd write equals to the natural logarithm of the modulus of, and it would be 4 plus 1 squared over 4 subtract 2. And then I'd close my modular symbols, and then write subtract, and substitute in my other limit 3. So I'd have a natural logarithm of the modulus of, and it would be 3 plus 1 squared over 3 subtract 2, like that. Then close my modular symbols. So the expectation for these questions is that you give your answer as an exact value, and the question will usually ask for that. So what you can't do is just put this whole calculation into the calculator, because you will not get an exact value. What you're going to have to do is go to what is within each logarithm and simplify it. So you could start by going to the first logarithm and putting this into the calculator. So we get the natural logarithm of, and actually we probably don't need the calculator for this one because it is a fairly straightforward calculation. 4 plus 1 is 5, so 5 squared is 25, and then 4 subtract 2 is just 2. Now, because that's come out as positive, we don't actually need the modular symbols anymore. I could just put in regular parentheses because the modular symbols won't have any impact if it's positive. Now let's move on to my other logarithm, Okay, and we have 3 plus 1, which is 4 squared, so 16. And then 3 subtract 2, which is just 1, so we get 16 over 1, which is of course just 16. And once again, this is positive, so I just need regular parentheses. And then what we can now do is combine this into a single logarithm because we got subtraction. So we're just going to divide what is inside my logarithms. So we'd have a natural logarithm of, and it's going to be the 25 over 2 divided by 16, which is equal to 25 over 32. So this here would be my final answer to the definite integral. Now let's have a look at a more complicated question. So here's the next question. We've got another fraction, and this time the denominator is already factorized into linear factors. That's usually a big hint that you're going to have to use partial fractions. Now, the one thing I would check before you jump into partial fractions is, do you have an algebraic improper fraction? Well, if we look at the highest power in the numerator, okay, the highest power of x in the numerator would be 2. And if we look for the highest power in the denominator, we just have to imagine what would we get if we expanded the brackets. And I believe the highest power we'd get if we expand the brackets would be an x cubed term. Okay, so therefore the highest power in the denominator would be the 3. So therefore the highest power in the numerator is not the same as or greater than the highest power in the denominator. So we don't have an algebraic improper fraction. So let's get started with our partial fractions. So what I'm going to do is write out my fraction here. So 8x squared, take 19x plus 1, divided by the 2x plus 1, multiplied by x subtract 2 squared. Now, because our denominator would be a cubic, okay, we're going to need 3 fractions that we're going to split this into. Okay, so I'm going to write this is identical to, and we're going to draw out my 3 fractions. And now let's select my denominators. So to do that, we have to look at the linear factors we have in the denominator of the original fraction. So we got a 2x plus 1, so that's going to be one of my denominators. And then we have an x subtract 2, which is raised to the power of 2. So therefore, one of my fractions are going to have a denominator of just x subtract 2 to the power of 1. And then the other one is going to be the x subtract 2, but to the power of 2 instead. And of course, these are being added together. And our numerators are going to be constants. So we'll call the first numerator A, the next one B, and then the final one C. Now our next step is to add all of these fractions on the right-hand side together with a common denominator. But let's just speed things up a little bit, given that we're going to end up comparing the numerator of the right-hand side with the numerator of the left-hand side. So I'm going to write out the numerator of the left-hand side, 8x squared, take 19x plus 1. And say that's identical to, and let's start thinking about what the numerator of the right-hand side will look like. To do that, we have to think about what are we going to multiply the first fraction by on the numerator and denominator to get our common denominator, which is going to be what we have in the denominator of the original fraction. So we've already got a 2x plus 1 here, which matches with this here. So therefore, I'm going to multiply our numerator and denominator by the x subtract 2 squared. Okay, so therefore the a is going to end up getting multiplied by an x subtract 2 squared like that. Now let's move on to my next fraction. So in my next fraction, the denominator is x subtract 2. Okay, so that matches with this here, but we still need to make the power squared. So therefore we're going to have to multiply by x subtract 2. But we also need the 2x plus 1. So what's going to end up happening is the b is going to be multiplied by x subtract 2 to the power of 1, and then 2x plus 1. So now let's have a look at our final fraction. Our denominator of our final fraction is the x subtract 2 to the power of 2, which matches with the x subtract 2 to the power of 2 from the original fraction we started with. The only thing that we additionally need to get in there is the 2x plus 1. So we'd have to multiply the numerator and denominator by 2x plus 1. So this c here is going to end up getting multiplied by 2x plus 1. So now we have the identity set up that's going to help us find a, b, and c. We just have to think about which x values are we going to substitute into both sides. So if we look at our first term here and consider specifically the bracket, the x subtract 2, which value of x is going to make that equal to 0? Well, it's going to be x equals to 2. So we're going to consider when x is equal to 2. To do this, we're going to substitute the 2 into the left-hand side. So let's put that into the calculator. So we'd have 8 multiplied by 2 squared, subtract 19 times 2, and then plus 1, which gives me negative 5. Now we have to substitute the x equals 2 into the right-hand side of my identity. So if we consider our first term here, we have an x subtract 2 multiplying into it, so that's going to become 0. And of course, 0 times anything is just 0, so that term is going to vanish. But if we look at the next term along here, we've also got an x subtract 2 here, so similar is going to happen there. We're going to end up with 0b, which is of course 0. So therefore, we only have to concentrate on my final term. Now, when I substitute x equals 2 into here, we're going to get 2 times 2, which is 4, plus 1, which is 5. So we're going to end up with 5 times c. And therefore, we can find c by dividing by 5 on both sides. So we would get c is equal to negative 1. Now let's consider which other x value we could substitute in to turn one of our brackets into 0. So the other bracket we have on the right-hand side is the 2x plus 1. So if I set the 2x plus 1 equal to 0 and rearrange to find x, we get 2x is equal to negative 1 and x is equal to negative a half. Therefore, when I substitute negative a half into 2x plus 1, we will get 0. So I'm going to consider when x is equal to negative a half. So let's start by substituting the negative a half into the left-hand side of my identity over here. So we would have 8 multiplied by negative a half raised to the power of 2. Subtract 19 times negative a half. And that would give me, once we add 1 on, 25 over 2. Now we have to substitute the negative a half into the right-hand side of my identity. Now, if we consider the terms with 2x plus 1 multiplying into them, so that's this term here and this term here, they're going to come out as 0, so we could ignore those and therefore just focus on this term here. Okay, we're just going to have to replace this x here with a negative a half. Okay, so we're going to get a multiplied by negative a half, subtract 2 to the power of 2, and that would give me 25 over 4 lots of a. So now we have an equation which we can use to find a, and to do that we're going to have to divide by 25 over 4 on both sides. So if we do 25 over 2 divided by 25 over 4, we get an answer of a being equal to 2. So we found a and c, but we still need to find b. Now, if you look for more brackets that we can try and make equal to 0, we don't have any more. We've used both of them that are present, the x subtract 2, which is there, and then the 2x plus 1, which is there and there. So therefore, what we're going to have to do now is just pick some other value for x to substitute into both sides. However, before we do that, what I want to do to make things a little bit easier and have fewer unknowns is I'm going to substitute c equals negative 1 and a equals 2 into my identity because we know each of their values. So in place of the a here, which I'm going to rub off, we're going to put a 2. And in place of the c over here, we're going to put a negative 1. So actually, I'm just going to take the plus off and just put a subtract symbol there like that. So now let's pick which x value we're going to substitute into both sides of my identity. And as I said, you can pick any x value. So I'm just going to go when x is equal to 0. Okay, because often 0 is quite a straightforward value to substitute in because anything times 0 is 0. Okay, so let's substitute x equals 0 into the left-hand side of my identity. Well, anything multiplied by x is just going to become 0. So 8x squared is going to be 0. But negative 19x is going to be 0. So we're just going to be left with the positive 1. Now let's do the right-hand side of my identity. So if I put 0 in for this x, we're just going to be left with negative 2 inside the brackets. And if we square negative 2, we get positive 4, which we then multiply by this 2. So that's going to give me positive 8. Now let's look at the next term along. So when I substitute 0 into this bracket, we're going to get negative 2. If I substitute 0 into this bracket, well, 2x is going to become 0. So we're just left with the plus 1. So we're left with 1 times negative 2 times b, which is negative 2b. Now let's move on to my final term. Well, when I substitute 0 into 2x plus 1, we've already discussed that. We're just going to be left with 1. So we're going to have subtract 1 like this. Now we have an equation here that we can solve for b. So what I'm going to do is simplify the right hand side. So we get 1 is equal to, and we got the 8, subtract the 1. So that's going to leave me with 7, and then subtract 2b. And then we're going to subtract the 7 to the other side. So we get negative 6 is equal to negative 2b. And then we're going to divide by the negative 2. So we're going to be left with b equaling positive 3. So I've got my final value for the numerators of my partial fractions. So now let's substitute my a, b, and c into my partial fractions. So I'm going to rub out my numerators, the a, the b, and the c. And we can substitute in my value for a, which was 2, our value for b, which was 3, and our value for c, which is negative 1. Now we could put this negative sign in front of the fraction instead. So what I could do is rub out the negative 1 and the plus here, put a negative sign here, and then leave the positive 1 in the numerator. Now let's have a go at carrying out the integration. So what I'm now going to do is rewrite my original integral using the partial fractions I've found. So this will become the integral of, and it's going to be these 3 fractions here. Okay, so we got the 2 over 2x plus 1 plus the 3 over x subtract 2, and then finally subtract the 1 over x subtract 2 to the power of 2. And because we got 3 different terms, they're split by addition and subtraction, I'll put them in brackets and then write the dx here. Now, because the 3 fractions are split by addition and subtraction, we can concentrate on integrating each one individually. Now, if we look at our first 2 fractions, our denominators are raised to the power of 1. So for these, we should be considering the natural logarithm and the reverse chain rule. Okay, so if I look at my first one, my first denominator here, if I differentiate 2x plus 1, we would get 2, which is a perfect match of my numerator. So therefore, our integral for this fraction would be the natural logarithm of the modulus of 2x plus 1, our denominator, and we'll just leave a 1 in front of my natural logarithm because the denominator derivative was a perfect match of the numerator. So we don't actually have to write the 1 there. We're just going to leave it as the natural logarithm of the modulus of 2x plus 1. Now let's look at my second partial fraction. Our denominator is x subtract 2. When I differentiate that, I'm going to get positive 1. If I compare that to my numerator of 3, well, I'd have to multiply by 3. So clearly they're numerical multiples, so we're good to use the natural logarithm, but we're going to have to write the 3 in front multiplying our natural logarithm. So I'd write plus 3 lots of the natural logarithm of the modulus of our denominator x subtract 2 like that. Now let's have a look at my third partial fraction, which is a little bit different. So looking at our third fraction, our denominator is raised to the power of 2. Therefore, we're not going to want to use the natural logarithm because if you differentiate your denominator, you will not get a numerical multiple of your numerator. Instead, we're going to want to use indice laws to rewrite this so that the x subtracts 2 squared is no longer in the denominator. So what I would do is take my numerator, which is essentially the negative 1, and I would write it as multiplied by our denominator x subtract 2, but raised to the power of negative 2 instead. Now let's consider whether we can use the reverse chain rule. So if we look at what is inside my bracket, the x subtract 2, if I differentiate that, I get 1. And if we compare that to what is multiplying my bracket, the negative 1, they are numerical multiples of each other. Therefore, we can use the reverse chain rule, which will be the case once you've done partial fractions and you get a denominator raised to a power other than 1. So now let's proceed with carrying out my reverse chain rule. Well, when that happens, I know that my bracket stays the same. So the x subtract 2 will remain the same. Our power, negative 2, will increase by 1. So we get a power of negative 1. And then what I need to do is take the original negative 1 multiplying my bracket. And we're going to divide it by the derivative of my bracket, which was the 1. And then we're also going to divide it by our new power, this negative 1 here. So I'm going to multiply by negative 1 in the denominator of this fraction here. Now let's go through and simplify, and let's not forget our plus c. Okay, because what we're going to get is the natural logarithm of the modulus of 2x plus 1 plus 3 times the natural logarithm of the modulus of x subtract 2. And then this fraction here is just going to simplify to positive 1. So we'd have plus x subtract 2 to the power of negative 1 plus c, like that. Now let's also consider how we can combine our two log terms together. Now we have a plus between them, so we could use our addition law of logs, but before we do that, we're going to have to deal with the 3 here. We're going to have to bring it in as a power. So we would get the natural logarithm of the modulus of 2x plus 1, and then plus the natural logarithm of the modulus of x subtract 2, and that's going to be raised to the power of 3, and then plus our x subtract 2 raised to the power of negative 1 plus c. Now that we brought our power of 3 in, we can now use our addition law of logs to combine our first two terms. Okay, what is inside the logarithms are going to multiply together. So therefore, what we're going to get is the natural logarithm of 2x plus 1 multiplied by the x subtract 2 to the power of 3. And then we're going to get plus our other term, which is x subtract 2 raised to the power of negative 1 plus c, like that. And that's as far as you'd be expected to simplify. Now let's have a look at a definite integral based off this question. So here we've got our definite integral because we've now got limits, but the fraction that we're actually integrating is the same, so we can make use of our answer from the previous part. So what I'm going to do is write equals to, and then I'm going to write square brackets, and I'm going to write the result that we've got up here in the square brackets. We don't need the plus c because it's a definite integral. So we've got the natural logarithm of the modulus of 2x plus 1 multiplied by x subtract 2 to the power of 3, and then plus the x subtract 2 to the power of negative 1, which you could write as 1 over x subtract 2 if you want. And then we're going to close our square brackets and then put my limits of 5 and 3 here and here. Now let's start substituting my limits in. So we're going to start with the 5, our upper limit as usual. So we're going to write equals to, and then we're going to substitute in the 5. So we get the natural logarithm of the modulus of 2 lots of 5 plus 1 multiplied by 5, subtract 2 to the power of 3, and then close my modulus, and then plus 1 divided by 5 subtract 2, like that. And I will put that all in brackets because that's my complete substitution with the 5. Now let's do the 3, our lower limit. Okay, so we're going to write subtract and then open brackets, and then we're going to write the same expression out again, but with a 3 subbed in place of the 5. So we'd have a natural logarithm of the modulus of 2 lots of 3 plus 1, and then 3 subtract 2 to the power of 3, and then close my modulus, and then plus 1 divided by 3 subtract 2, like that. So that's my complete substitution. Now usually you're expected to give your answer as an exact value, so you can't put the whole thing in the calculator. So what I'm going to do is I'm going to simplify this part, this part, this part, and this part. Okay, and you can use the calculator to assist you with that, as it will give you exact values for those parts. So we'd have a natural logarithm of the modulus of, and I'm going to put that calculation underlined in the calculator, which gives me 297, which is positive, so therefore we don't actually need the modular symbols anymore. And then the next fraction I have there, well, that's fairly straightforward. 1 over 5 subtract 2 just becomes 1 over 3. And then subtract. And I'm going to put my next underlined calculation in my natural logarithm into the calculator, which just gives me 7, which was actually a straightforward calculation. And once again, it's positive, so we no longer need modular symbols, so we'll just put in regular parentheses. And then for the plus 1 over 3 subtract 2, well, that's just going to become 1 over 1, which is 1. So plus 1, like that. Now let's think about which terms we can simplify together here. Okay, we'll start with our natural logarithm terms, so this one here and this one here, and they're being subtracted. Therefore, I can divide the 297 and the 7. So I would get the natural logarithm of 297 divided by 7. And then we've also got the 1/3 subtract the 1. So that's going to give me negative 2/3. And this here would be my final answer as an exact value. There's nothing more that you can do with that. Now let's have a look at an even more challenging question. So here's our final question. And once again, we've got a fraction and the denominator is factorized. So that is a hint we're going to have to use partial fractions. However, like before, let's just check, do we have an algebraic improper fraction? So if we look at the numerator and identify the highest power of x, the highest power of x is a 2. But if we look at my denominator, okay, it's currently factorized, but if we expand the brackets, the highest power of x that we are going to get would be x squared. So therefore, the highest power in the numerator is the same as or greater than the highest power in the denominator. Therefore, we do have an algebraic improper fraction. So what we need to start by doing is doing algebraic division. So what I'm going to do is expand my denominator, as I'd prefer to have it expanded before I do my division. So we'd have 3x squared, subtract 3x, subtract 2, divided by, and when I expand the brackets, I believe I get x squared, take 3x, plus 2, like that. Now let's set up my algebraic division. So it's going to be my numerator, which is 3x squared, take 3x, take 2, divided by my denominator, which is the x squared, take 3x, plus 2, like that. Now to start my process of division, we're going to do the 3x squared divided by the x squared. So that's going to give me 3, so that's a constant. So I'm going to put it in the far right in the constants column. Then we're going to take that plus 3, and we're going to multiply it by this expression here. So 3 times x squared would give me 3x squared. 3 times the negative 3x would give me negative 9x. And then 3 times the positive 2 would give me positive 6. Like that. And then we're going to subtract to find my remainder. So I'm going to subtract, and we have 3x squared subtract 3x squared, which is 0x squared. Then we have negative 3x subtract negative 9x. So if we're subtracting a negative, we're adding. So we get negative 3x plus 9x, which would give me positive 6x. And then finally, we have the negative 2 subtract positive 6. So that's going to give me negative 8. Then if we look at what we've got, our power of x here is 1. And then the highest power of x over in our divisor is x squared. So our power has gone below the x squared. So therefore our division terminates there. So now we can write out our answer to the division. I can say that the 3x squared subtract 3x subtract 2 divided by the x squared subtract 3x plus 2 would be equal to, and it's going to be our quotient, which is written up here, so the 3, plus our remainder, which is the 6x subtract 8. And the idea is that 6x subtract 8 has not been divided by our divisor over here. So we need to write the 6x subtract 8 over the x squared, take 3x plus 2 like that. So now using what we've got here, we can go back and rewrite my integral. So what I can do is replace my fraction here with its rewritten version using the algebraic division down here. So we would get equals to the integral of, and it's going to be 3 plus 6x subtract 8 over x squared take 3x plus 2. We've got multiple terms, so we'll put it in brackets and then write dx. Now what we have to consider is how we're going to integrate both of the two terms that we have here, because we've got the 3 and then we've also got this fraction here. Now the 3 is just a constant, so that's just going to integrate to 3x. What we need to focus on is this fraction here. So let's go through our methods for integrating fractions. So our denominator has 3 terms in it, so we're not going to want to split up our fraction into multiple fractions involving the same denominator, because we usually do that when we've only got one term. Our denominator is raised to the power of 1, so therefore we're not going to want to use indice laws, because then we'll get a power of negative 1, which we don't want when we're integrating. So let's consider whether we can use the natural logarithm. So to do that, I'm going to take my denominator and I'm going to differentiate it. So that's going to give me 2x subtract 3. And then we're going to compare what we've got here with my numerator and ask ourselves, are they numerical multiples of each other? Well, to get from 2x to 6x, we'd have to multiply by 3. However, to get from negative 3 to negative 8, we'd have to multiply by a number other than 3. So they are not numerical multiples of each other. Then we'd usually consider, do we have ourselves an algebraic improper fraction? However, we know that's not going to be the case because we already dealt with that issue with the original fraction that we had. So our next strategy to consider would be partial fractions. So whether we can use partial fractions depends on whether we can factorize the denominator into linear factors. Well, we know that we can do that because in the original question, the x squared subtract 3x plus 2 was factorized as the x subtract 1 times x subtract 2. So I'm going to write that back in. So I've got equals to the integral of, and it's got 3 plus 6x subtract 8 divided by the x subtract 1 multiplied by x subtract 2. So now what we need to do is rewrite that fraction in terms of its partial fractions. So let's get started with that. So I'm going to write my fraction here. So 6x subtract 8 divided by x take 1 multiplied by x take 2. And when I split this into partial fractions, we're going to have two fractions. One denominator is going to be the x subtract 1. And then the other denominator is going to be the x subtract 2. Now write in my plus, and my numerators will be constants, so we'll call it a and b. Then our next step is to add the fractions on the right hand side using a common denominator. However, we do know we're going to end up comparing our numerators, so I'm going to take my numerator on the left hand side, the 6x subtract 8, and write it here, and write that it's identical to. And what we just need to think about is what are we going to multiply the a by and what are we going to multiply the b by in the process of getting our common denominator. Well, our a is going to end up being multiplied by the x subtract 2. So we're going to have a, lots of x subtract 2. And then my b is going to get multiplied by the x subtract 1. So I'm going to write plus b multiplied by x subtract 1 like that. Now let's consider which x values we're going to substitute into both sides of my identity, which is going to make it so one of my two brackets are equal to 0. So let's start with the x subtract 2. Well, we'd have to substitute x equals 2 in. So let's consider when x is equal to 2. So when I substitute the x equals 2 into the left-hand side, we're going to get 6 times 2, which is 12, subtract 8, which is 4. And then on my right-hand side, my first term is going to become 0 when we substitute 2 in. So we only have to concentrate on my second term here. When I substitute 2 into my bracket, we'd have 2 subtract 1, which is just 1. So we get 1 lot of b. So therefore, b is equal to 4. Now let's consider what is going to make my second bracket equal to 0. So that would be when x is equal to 1. So let's substitute 1 into both sides of my identity. So if I do it on the left-hand side, we get 6 times 1, which is 6, subtract 8, which is negative 2. And then on my right-hand side, my second term over here is going to be 0, because we know x equals 1 makes the bracket 0. For my first term here, when we substitute x equals 1 into the bracket, we're going to have 1 subtract 2, which is negative 1, times a gives us negative a. Now, if we multiply it by negative 1 on both sides here, we're going to get positive a is equal to 2. So we've got our value for a. So we can now go back to my partial fractions and rub out my numerators a and b and substitute in my results for a and b. So for a, we got 2, and for b, we got 4. Now we can return and finish off the integral. So let's rewrite the fraction in my integral using the partial fractions I found over here. Okay, so I'd have the integral of, and it's still going to be 3, and then plus, and then my first fraction is 2 over x subtract 1, and then my next one is 4 over x subtract 2. Close brackets and then dx. Now let's go through and integrate each term. So starting with the 3, well, that's just a constant that integrates to 3x as discussed previously. When looking at this fraction here, the denominator is raised to the power of 1, so this is going to be a scenario where we use the natural logarithm. Okay, if I differentiate my denominator, that would give me 1. If I compare that to my numerator, where we've got 2, well, I'd have to multiply by 2, so we're going to make use of that in my final answer. So I'm going to write plus 2 lots of the natural logarithm of the modulus of my denominator x subtract 1. Then let's have a look at my final fraction, okay, which is the 4 over x subtract 2. Well, if I differentiate my denominator, I would get 1. And comparing that to my numerator of 4, well, I'd have to multiply by 4 to get there. So we're going to make use of that times 4 in my answer. It would be plus 4 lots of the natural logarithm of the modulus of x subtract 2. And then, of course, we need our plus c. Now, the last thing we might do is try and combine our two natural logarithm terms. So the first thing I'm going to do is bring in the 2 and the 4 as a power. So we would have 3x plus the natural logarithm of the modulus of x subtract 1 squared, and then plus the natural logarithm of the modulus of the x subtract 2 raised to the power of 4, like that, and then plus c. Now, because the x subtract 1 and the x subtract 2 inside our natural logarithms are both raised to even powers, it means they're always going to be positive. So therefore, we don't need the modulus symbols technically. Okay, so we can actually drop the modulus symbols here and drop the modulus symbols there. Now what we can do is try and use the addition law of logarithms, which means the x subtract 1 squared is going to multiply by the x subtract 2 to the power of 4. So we get plus the natural logarithm of, and it's going to be x subtract 1 squared times x subtract 2 to the power of 4, and then plus c. And that would be my final answer.